Okay, so based on the limited number of Unit 6 tests that I've had turned in, stoichiometry is a concept in chemistry that's very difficult. Okay, so if you're finding this harder than things earlier in the block, it's not surprising. You just gotta, put a little bit more effort into it. So based on the test, these were the major concepts that were missed. How to use Avogadro's number, kind of what it's for, and then how to calculate molar masses, formula masses, and stoichiometry calculations. Okay, so the mole, it's like the word a dozen. When you say you have a dozen of something, that communicates to everybody that you have 12 of them. All right? When you say you have a mole of something, that communicates it to a specific number, how many you have of it. It just so happens to be this gigantic, huge number, 6.022 times 10 to the 23rd particles. It's gigantic. Okay? So using this number, really it's only useful for atoms. If you try to count a mole of something else, it probably won't even exist. So we use it to count a reasonable amount of atoms, something we can actually see. Some common things that you might run into when doing this, there's a few elements that are called diatomic elements, meaning they make a molecule of 2 atoms each. So for example, these particular elements, oxygen gas, hydrogen gas, nitrogen gas, fluorine gas, chlorine gas, bromine liquid, or iodine solid, a mole of those molecules has twice as many atoms as a mole of anything else because they're always in pairs. So a mole of the first atom is attached to a mole of the second one. So that number, the 1.204 times 10 to the 24th is a typo, is something you might want to remember. Another thing that you might do with this is some conversion type stuff. So if you know you have 1 mole, and we know that 1 mole is equal to 6.02 times 10 to the 23rd, that's how many particles? 6.02 times 10 to the 23rd particles. Alright, so you can keep setting this up. 1 mole is 6.02 times 10 to the 23rd. Now, when you get to this point, if you don't have a calculator handy that can do the exponent stuff in there, ignore the exponent for now. You can do 3 times 6.02, which gives you 18.06, which would then just become, so the 18.06, to write that in scientific notation, we're going to have to move the decimal once. So it's going to be 1.806, and then that decimal move adds another number to the exponent, times 10 to the 24th particles. Honestly, the questions aren't so tricky that they change the exponent number. The exponent number is always correct. So just do the 2.5, 1 mole, 6.02 times 10 to the 23rd. So 2.5 times 6, .02, that's going to give you 15, so you're looking for an answer that's like 1.5 times 10 to the 24th. Okay, so these calculations aren't too bad. Another thing that came up as being an issue for some people was molar mass or formula mass. So the masses on the periodic table, those atomic masses, those tell you how many grams a mole of that element weighs. Okay, so if you had a mole of just oxygen atoms, it would weigh 16 grams. If you had a mole of oxygen gas, which was O2, that'd be 32 grams, so you multiply it by 2. A mole of carbon atoms is 12 grams. A mole of chlorine atoms is 35 grams. Okay, so once you know that a mole of just one kind of that, a mole of just one of those atoms has the mass of what's on the table, you can easily figure out the formula mass of a chemical formula. You just add the numbers together. Alright, so carbon dioxide is something we breathe out. If you wanted to know the molar mass or formula mass of carbon dioxide, you're going to take one carbon, so 12, and two oxygens, 16 and 16, and add them together. So the molar mass or formula mass of carbon dioxide is 44 grams per mole. So for ammonia, you'd take the 14 for nitrogen and then the 1 for hydrogen, but you do that 3 times to get 17 grams per mole. And for iron hydroxide, if you look at the periodic table, iron, I believe, is 56 grams. All right, and then because the OH is inside parentheses with that little 3, you're actually going to have 3 oxygens and 3 hydrogens. So that ends up being 107 grams per mole. All right. So the last kind of sticking point, and this is definitely the hardest thing out of this unit, is the stoichiometry type problems. Okay, this diagram comes in really handy. If you have a chance, take a screenshot, print it off, hold it nearby, because it gives you all the conversions you need, all the steps that you need, and know that every stoichiometry problem, unless it's just asking about moles, is going to take 1, 2, 3 steps. Okay, first step, you convert from whatever you're in to moles. All right, middle step, you use the molar ratio. You convert from moles of substance A to moles of substance B. And then the third step, you convert out of moles to whatever the question's asking about. So, for example here, if you have 79.1 grams of HCl, first I need to convert that to moles. So I need to know my molar mass of HCl. Chlorine has a mass of 35, and hydrogen a mass of 1, so that's going to be 36 grams of hydrochloric acid in 1 mole of hydrochloric acid. And then in the molar ratio step, that's where the numbers from the balanced equation come in. We're going to have 2 moles of HCl on the bottom because there's a 2 in front of it in the equation. And we're going to hydrogen, which there's no number in front of it, so that means 1 mole of hydrogen. And then in that third step, the question is about how many liters of H2 gas. So 1 mole of H2 has to go in the bottom to cancel out, and we know 1 mole of any gas is 22.4 liters. So I'm going to double check my work. Grams of hydrochloric acid cancel out. Moles of hydrochloric acid cancel out. Moles of hydrogen cancel out. My final unit is liters, which is what the question asked for. So since my work checks out, now I just do the math. I'm going to do 79.1 times 22.4, because that's all on the top. I'm ignoring the ones because of multiplying by 1 doesn't change anything. And then I'm going to divide by the numbers on the bottom, so divided by 36, and divide by 2, and I get 24.6 liters of H2. That's my final answer. A few more examples, just so you have plenty to go by. One of these should be similar to what you're doing there, so just kind of follow along and change the numbers for the molecules that you're working with. So if you have 45 grams of aluminum and excess oxygen, what mass of aluminum oxide will you make? So I have 45 grams of aluminum. And then aluminum has a molar mass of 27 grams of aluminum for every mole of aluminum. Then I hit that molar ratio step. I have 4 moles of aluminum, and for every 4 moles of aluminum I should make 2 moles of aluminum oxide. And then it says what mass of aluminum oxide will I make. So I have to put 1 mole on the bottom. And then I need to figure out my molar mass there. So I'm going to have 27 times 2 plus 16 times 3, which is 102 grams of aluminum oxide. Alright, I'm going to double check my work. Grams of aluminum cancel, moles of aluminum cancel, moles of aluminum oxide cancel. I'm left with grams of aluminum oxide, which is what the question was asking for. So now I'm going to do my math. I have 45 times 2 times 102 divided by 27 divided by 4. And that gives me 85 grams aluminum oxide. Alright, so last one. If you have 49.5 liters of oxygen gas, excess aluminum, what mass of aluminum oxide will you make? So here I have 49.5 liters of O2. I'm going to convert that to moles. I know that a mole of anything, regardless of its formula, is 22.4 liters, and that's equal to 1 mole. And then I have my molar ratio, 3 moles of O2 in the bottom, so I can cancel that out. And then it's asking about mass of aluminum oxide, so that's 2 moles Al2O3. And then 1 mole Al2O3. Then I just solved this on the other side. It's 102 grams aluminum oxide in a mole. So, double check my work. I have liters of O2 canceled, moles of O2 canceled, moles of aluminum oxide canceled, and I'm left with grams of aluminum oxide, which is what the question asked for. So now I just do my math. 49.5 times 2 times 102 divided by 22.4 divided by 3 gives me 150 grams of aluminum oxide. So I hope this helps. This is definitely one of the more difficult tests in the unit, or in the course. So if you do decently well, good job.